Have you ever stopped to think about how your computer is streaming music, letting you browse the web, and running a word processor all at the same time? It really does feel like magic. But what's actually going on is this incredible illusion, a perfectly choreographed dance run by your operating system. So today, let's pull back the curtain and see how your computer actually juggles everything.
Right, so how on earth is this possible? The heart of your computer, the CPU, can really only do one single thing at any given microsecond. You can think of it like a world-class chef who can only chop one vegetable at a time. So how does the operating system, our master chef in this story, make it look like an entire 5-course meal is being prepared all at once? Well, it all starts with some serious organization.
To manage a totally chaotic kitchen, our master chef needs clear, well-defined recipes. And the operating system does the exact same thing, but its recipes are called processes. It takes every single program you want to run, your music player, your browser, and it packages each one up into a neat, manageable little unit.
And this is a really important point. A process isn't just the program file sitting on your hard drive. A process is a program that is actively running. It's a living, breathing thing that the operating system has to manage. It's like the OS taking your Spotify app icon and transforming it into the actual live task that's pumping out your music right now.
Now, to keep everything straight, the OS breaks down every single process into a consistent structure, kind of like a standardized recipe card. You've got the text section, that's basically the recipe instructions. The data section holds the main ingredients, what we call global variables. The heap is like a big pantry for grabbing extra memory whenever it's needed. And the stack? That's a temporary workspace for all the quick little tasks. Every single process you run is built just like this.
The thing is, processes aren't static. They're alive. They move through this whole life cycle. A process is created, then it enters a ready state, just waiting for its turn. It gets some time on the CPU to run, maybe gets put in a waiting state for a file to download, and then eventually it's terminated. But look at that ready state. This is where a whole new problem pops up. When you have dozens of processes all lined up, all ready to go, how does the OS decide who gets to go next? And that question leads us right into our next big topic: CPU scheduling. So our master chef, the operating system, has this whole stack of recipes, our processes, all prepped and ready. Now it needs a strategy to decide which one to hand off to the cook, the CPU, at any given moment. The part of the OS that makes this call is called the CPU scheduler. Its entire job is to look at that ready queue, that line of processes waiting for their turn, and pick one to give to the CPU. And this happens fast. We're talking hundreds, maybe even thousands of times every second. That rapid-fire switching is the secret sauce that creates that powerful illusion of multitasking. But how does it choose? Well, there are a bunch of different strategies. A really common one is first come, first served. It's simple, it's fair, just like a line at the deli. But fair doesn't always mean efficient. An alternative is shortest job first, which always picks the quickest task to run. This is actually proven to be the most efficient way to keep wait times low, but it has one massive catch. It basically requires a crystal ball. You have to know the future, which is, kind of tricky. And you can see the difference right here in the numbers. With the exact same set of tasks, the average wait time for first come, first served is 6.2 milliseconds. But by prioritizing the shorter jobs with SJF, that average drops all the way down to just 3.8 milliseconds. That's a huge difference. The choice of scheduling algorithm has a massive, direct impact on how fast and responsive your computer feels. Okay, so we've organized our tasks into processes, and we have a schedule for running them. It seems like we've got it all figured out. But now we hit the really dangerous part. What happens when two processes need to access the same shared resource at the exact same time? This is where everything can go horribly wrong. Imagine two assistant chefs in our kitchen, and they both reach for the last jar of some super rare spice. If they don't coordinate, they could knock it over, spill it everywhere, and completely ruin the dish. In the world of computing, this is called the critical section problem, and the outcome is often data corruption. Let's make this super clear with a classic but dangerous example of something called a race condition. So, picture a shared bank account. Initial balance, $100. Okay, now at the exact same instant, Process A decides it wants to deposit $50, and Process B wants to withdraw $30. Here's the critical part. They both read the initial balance of $100 at the same time, and the race is on.
So process A does its math, 100 plus 50, and it writes a new balance of $150. But at almost the very same moment, process B has done its calculation, 100 minus 30, and it writes its new balance, $70. So what's the final balance? Is it $150 or is it $70? The correct answer, of course, should be $120. But because of this race, the final result is just whichever process happened to finish writing last. Our data is now inconsistent, it's totally wrong, it's corrupt. This is the disaster we absolutely have to avoid.
So how do we fix this mess? With a really elegant and clever tool called a semaphore. Honestly, the best way to think about a semaphore is like putting an in-use or occupied sign on a bathroom door. It's a simple idea, but it's incredibly powerful for creating order out of chaos.
Here's how it works. Before a process can access that shared data, its critical section, it performs a wait operation. It's like checking if the bathroom door is locked. If it's free, cool, it goes in and gets the lock. If not, the OS is smart. It just puts the process to sleep, no wasted energy checking over and over again. Then, when it's all done, it performs a signal operation, unlocking the door, which tells the OS to wake up the next process in line. One at a time, orderly, chaos avoided. So there you have it. It's these three big ideas working together in perfect harmony. Processes to keep everything organized, scheduling to act as the traffic cop, and synchronization to make sure nobody crashes into each other. Together, they create that smooth, seamless illusion of multitasking that we all just take for granted.
And you know, this isn't just about computers. This fundamental problem of managing a ton of things happening at once to prevent chaos, it's absolutely everywhere. We're talking about air traffic control, stock market trading, you name it. It's a foundational challenge in any complex system. It really makes you wonder, what other examples of this kind of massive juggling act can you spot in the world around you?